We are starting the webinar, and I'm speaking on behalf of the Institution of Aquaculture Singapore. Before I start, I'd like to introduce Dr. Tzachi Samocha. Dr. Tzachi Samocha is a recently retired Regents Fellow and Professor with the Texas A&M AgriLife Research. After obtaining his Ph.D. from Tel Aviv University, Israel, he joined National Center for Mariculture in Eilat, Israel, where he served as head of Stream Research Unit from 1980 to 1988. In 1988, he joined the Texas A&M University System for 27 years, where he served as Director of R&D at the AgriLife Research Mariculture Lab, Corpus Christi, Texas. His research scope covered numerous areas, including induced maturation, larval rearing, and nutrition of several peanut shrimp species. In addition, he performed numerous studies in indoor raceways and outdoor ponds to develop new concepts in sustainable, biosecured, biofloc-dominated intensive nursery and grow system. He has conducted research on aquaculture effort, water remediation using integrated multi-trophic aquaculture (IMTA) system, halophyte, and microalgae. As part of his responsibility as Director of R&D, he was heavily involved in technology transfer to commercial producers, industrial-related businesses. Dr. Samocha is currently providing consulting and training services on different aspects of shrimp production to clients in different parts of the world. Okay, without further ado, I'd like to introduce Dr. Samocha to do his presentation, and also I'd like to inform our participants, please mute yourself so that there should be no disturbances during the presentation. You can ask the question after Dr. Samocha has finished his presentation. Thank you. Dr. Samocha, please.
Thank you very much. Can you tell me if everybody can see the screen? Can you see the screen right now?
I can see the screen, yes. Everybody should see the screen.
Okay, good. Thank you very much, Mr. Lim. I want to thank you for organizing this webinar, and I hope that at the end of this short presentation, you guys will have a better understanding of the concept of biofloc, which is one of the issue that quite a few people in different parts of the world are trying to practice, and sometimes they do have some issue how to manage it. So I hope with some of the information that will be provided here, it will be easier. And I would also, throughout the presentation, elaborate a little bit more about the book or the manual that we have published that can be very useful for those of you which are interested in getting more in-depth information. As you can see, the topic of my presentation is Sustainable Biofloc System for Marine Shrimp. I'll be talking about design, operation, and some about the profitability. By no means I'll be able to cover the issue of profitability in such a short period of time. So bear this in mind, and hopefully in the future, we'll be able to organize more webinars with a focus on profitability and economic analysis, because the bottom line is the question whether or not you can make money from growing shrimp in this type of system. Moving into the first slide, which deals with the seafood deficit. We know that global seafood demand continue to increase, but supply is beyond maximum sustainable yield. Aquaculture's mission is to fill the seafood gap by sustainably increasing production. This is a goal of the producer, the retailer, and the consumer. Now, moving into practice, quite a few years have been in use, and this is the flow through and the problem associated with it these days. Traditional ponds rely on high water exchange. This is not biosecure, and it risks introducing pathogen to culture water, discharging contaminants to natural water, and escapee of non-native stock. True sustainability requires a shift to a circulating aquaculture system. there are two issues that you need to be concerned with the recirculating aquaculture system. The RAS expansion now proceeds slowly because discharging waste is less expensive than treating it. The solution is to fix by enforcing environmental standards. The other issue is the management, which requires higher technical expertise. And the way to fix it is to have people with much more advanced water quality training, so they will know how to deal with these issues. There is one option that can help us in terms of the water management, and this is the biofloc option. Basically, high-level biosecurity that can eliminate many problems with the flow through. Biofloc compromises from living, namely algae, bacteria, protozoan, and non-living like uneaten feed, waste component that you can find there. Now you can see on the right a graph in the picture, a different group of organisms that can be found as part of the biofloc: filamentous microorganisms, protozoan, nematode, copepod, rotifers. Again, they can be a different percentage of the biofloc depending on the condition of your system. Earlier work demonstrated the feasibility of high shrimp yields with no water exchange in biofloc-dominated system. And here I'm referring to it as a BFD. The BFD is designed to support high yield of fish or shrimp. It provides also stability of water quality. It requires constant oxygen supply and mixing. These are very important parameters that are crucial for the success of the biofloc system. Marine floc is rich in certain amino acid, but deficient in other. Also, it deficient in vitamin C. Indoor superintensive BFD perform better with a high quality feed to provide missing nutrients. So basically, although the BFD can provide some supplemental feed component, if you want to get very high or better result at high density, you may want to use also high quality and complete feed. Moving into the autotrophic and heterotrophic system. Autotrophs are primary producer like macroalgae, microalgae, and certain bacteria like the nitrifiers. Heterotrophs are all of the other organisms. Each type has specific metabolic requirement and predictable effect on water quality. By their nature, aquaculture systems are part autotroph and part heterotrophic, and therefore they are mixotrophic. In this respect, I want to mention that mixotrophic is a standard term in biology introduced in 1897 by Wilhelm Pfeffer, the German physiologist who also coined the term autotrophic and heterotrophic. The heterotrophic system compared to autotroph, heterotrophic system produces about 40 times more higher biomass of bacteria. It consumes oxygen at much higher rate. It produces also CO2 at much higher rate than the other system that I'll talk about it later. And it requires more management and resources. Heterotrophic system require very careful monitoring and control of organic carbon supplement, which is a driving force of the system. Now, comparing the heterotroph versus the autotrophic biofloc, the basic relationship that frame the water quality management. Basically, the heterotrophic system, for the requirement are ammonia, oxygen, alkalinity, and organic carbon. And as a result, you'll get products such as bacterial biomass and water and carbon dioxide. On the other hand, the autotrophic system, the requirements are ammonia, oxygen, and alkalinity. You see, it is missing the organic carbon. The product are bacterial biomass, water, and carbon dioxide. Remember, the amount of carbon dioxide that will be produced in the autotrophic system is lower than in the heterotrophic system. And of course, you'll get also nitrate, NO3. Moving into the mixotrophic approach, the Samocha, I call it the Samocha mixotrophic system, balances hetero and autotrophic system. And by that mean, what I like to see in my system, basically ammonia, oxygen, and alkalinity that is being controlled. And when the system is balanced, I do not need to add any organic carbon except for the one that comes with the feed. The main reason why the organic carbon that comes from feed, basically the heterotrophic bacteria will grab it and use it, while the nitrifying bacteria won't be able to compete on it for it. The product will be bacterial biomass, water, and carbon dioxide, and plus nitrate, as I mentioned earlier. Therefore, if you can imagine that your system is mixotrophic, basically what we are targeting is 1/3 of the activity will be taken care by heterotrophic bacteria that will metabolize the ammonia, while the other 2/3 of the ammonia will be metabolized by the autotrophic bacteria. Now, nitrate accumulates in both systems. It builds up more slowly in heterotrophic system. Thus, as in traditional recirculating aquaculture system, this system must remove nitrate with either a denitrification stage, water exchange, or algal or plant uptake. Here I'm moving to another section where I'll be describing different things. I'm just going to go through it very quickly, and then I will elaborate about it much more. Here you see the Sustainable Biofloc System, the manual that we have produced, the second edition that was published by Elsevier. And basically, if you are interested, you see on the bottom of this book, I also put an email address that if you click on it, you get the information where to purchase the book. And as I mentioned later, it's been published in e-form as well as in printed form. The contributors for this manual beside myself are Leandro Castro, Terry Hansen, Ingrid Lupach, David Pragnell, Nick Strasinik, and Granville Trees. In the next few slides, I'll be talking about objectives. I'll be talking about the 15 chapters that the book has, the appendices, the Excel sheets, the video, troubleshooting, and index. Chapter 1, which talks about introduction, history of outdoor and indoor shrimp biofloc system. Chapter 2, shrimp biology, morphology, life cycle, genetic, and nutrition. Chapter 3 will be dealing with the biofloc composition, structure, development, and benefit. 4 will be dealing with water characteristic, water sources, ionic composition, autotroph, heterotroph, mixotroph, and the nitrogen cycle. Chapter 5 deals with site selection and production system. 6 deals with system treatment and preparation. 7, water quality management, which is one of the major components of the biofloc. Nursery phase, chapter 8. Chapter 9, grow out phase. 10, shrimp harvest. 11, waste treatment and disposal. Again, very important aspect when you are dealing with a system that basically you need to deal with the waste that will be generated by the operation. Moving into disease and biosecurity, chapter 12, and chapter 13, economics of super intensive shrimp production system. Okay, now we start with whatever I mentioned earlier, but a little bit with more elaboration. Objective of this manual were to encourage expansion of biofloc-dominated system as developed by the Texas A&M AgriLife Research. funding for the work that we have done were provided by NOAA through the US Sea Grant. We had several participants in this particular project. It was the Auburn University, which contributed into the economic aspect of the system, Florida Organic Agriculture, and Texas Sea Grant Extension Service. The described biofloc-dominated system design and operation developed over 20 years at the Texas A&M AgriLife Research Mariculture Lab in Corpus Christi, Texas. It emphasizes the most recent Lithopeneus vanameae production and financial data. It's written in a non-academic style for a wide group of stakeholders, especially those interested in building a pilot biofloc-dominated system. It has 15 chapters plus appendages, Excel sheets, form, video, and extensive index. Chapter 1, as I mentioned earlier, deals with introduction, history of outdoor and indoor shrimp biofloc system. It provides several examples, but by no means cover all of the system or the biofloc system that are in use these days. Chapter 2 deals with the shrimp biology, especially for those which are not very much familiar with it, the morphology, like how would you distinguish between male and female, life cycle, species preference, genetic improvement, and nutrition, with emphasis on energy, protein, vitamin, and mineral requirement. Chapter 3 deals with the biofloc composition, structure, development, and benefit, especially dealing with the issue of feed, water quality, how it contributes to the stability, immune response, and so on. Water sources are dealt in Chapter 4. Here we are dealing with seawater, estuarine water, saline surface water, groundwater, fresh water. You have different types of water that you might consider for your operation. Needless to say that for the most part, if you have access to natural seawater, adequate in quality, this will be your best bet. Moving into the water characteristic, there are certain parameters you need to be aware of. The issue of dissolved oxygen, temperature, ammonia, nitrite, nitrate, phosphate, solid, not a suspended solid, settleable solid, turbidity, heavy metal, and trace element. Now, on the tables that you see here, I decided just to take very little information from the extensive information that appears under this section in the manual and show you some of the significant parameters that you may want to be aware of. And here I took the marine water, natural seawater, and I compared it to artificial seawater, high quality artificial seawater. You see the salinity, you see the pH, not much differences, alkalinity, chloride, sodium, potassium, magnesium, calcium, and sodium, and calcium and potassium. Now, one thing that you may want to see or watch for is the sodium-potassium ratio, magnesium, calcium, potassium, chloride, sodium, and magnesium ratio, and how it shows in different mixing. In the manual, you see different type of sea salt that we use. One thing that you certainly want to make sure that if you are working with artificial seawater, that you meet the requirement of the shrimp and you make sure that you won't have any heavy metal or any other toxicant that can be harmful for the shrimp. On the table on the bottom, you see some of the pesticide, PCBs, and chemical that you may want to make sure that your water will not basically have these components. As you may know that some of the people will go and get brine water from salt pan and use it. But you need to be aware of the fact that depending at what stage you pick the water, and because this may affect the composition of the brine that you have, and in some cases, you will have toxic impact on the shrimp that you are trying to grow. So not all brine are equal, and you need to be aware of it. Now, moving into one very important issue that basically control the biofloc among other, and this is the nitrogen cycle. Here we have 6 processes that I would like to summarize very briefly. First process is assimilation, which is the uptake of dissolved substances such as ammonia, nitrite, nitrate to build organic nitrogen compound such as protein by algae and certain bacteria. Moving into the ammonification, which is produces ammonia via breakdown of organic material by bacteria and ammonia excretion after metabolizing feed protein. Ammonium oxidation is the next one, which converts ammonia to nitrite, NO2, by bacteria. This process is more efficient between 7.8 to 8, and that's very important when you are trying to balance pH in your system. Bear in mind that the optimal for ammonia oxidation is 7.8 to 8. Now this process used as an energy source, the ammonia. They require free oxygen, bicarbonate as a carbon source, and this is the reason why you need to maintain adequate alkalinity in your culture water. Bear in mind that during this process, the pH and alkalinity been reduced, so you need to maintain them. Moving into nitrite oxidation, basically you take the NO2 and convert it to nitrate, which is a NO3, by bacteria that uses nitrite as an energy source. They require aerobic environment and function better at a pH of 7.3 to 7.5. The process has no effect on pH or alkalinity. So basically the impact on pH and alkalinity is only from the first stage, namely ammonia conversion to nitrite, which operate better at 7.8 to 8, while the nitrite oxidation is from 7.3 to 7.5, and this will not be reduced throughout the process. Ammonium oxidation and nitrite oxidation are also referred to as a nitrification, which removes ammonia and produces nitrate. Denitrification produces nitrogen gas from inorganic nitrogen compound with part escaping to the atmosphere, namely there is a nitrogen removal from the system. Denitrifying bacteria require an anoxic environment, unlike the oxidation in the conversion of ammonia to nitrate. Here you need anaerobic condition. So basically, you need to have also some other component like NO3, nitrate, or nitrite. Some denitrifiers are heterotroph that require also supplementation of organic matter and nitrate. The denitrification process raises the pH and increases alkalinity. So basically, when you are working with a biofloc system, pH and alkalinity tend to drop. Now, if you attach denitrification component to your biofloc system, you should be able to balance it, and whatever you loses from the ammonification and nitrification, you will be gaining it back with the denitrification. And finally, the nitrogen fixation, complete the nitrogen cycle by converting atmospheric or dissolved nitrogen gas into ammonia that becomes available for biological transformation. Continue about the chapter 4, the biofloc system. It depends on microbial activity in floc to remove ammonia. Some rely primarily on heterotrophic bacteria to transform ammonia into bacterial biomass that serve as a supplemental shrimp feed. So basically you can work with heterotrophic biofloc system, but you will see that I'm advocating a different approach. The Texas A&M AgriLife Research Mariculture Lab BFD system is different. It discourages heterotrophic bacterial dominance the flock. It encourages, on the other hand, a mix of hetero and heteroautotrophic bacterial flock. The BFD thus is a mixotrophic system. This approach is more efficient way to ensure high water quality and provide supplemental lateral feed, as you will see later in some of the examples that I'll be providing. Autotroph, heterotroph, and mixotroph may be unfamiliar term for some of you. They were coined, as I mentioned earlier, more than 120 years ago by German plant physiologist Wilhelm Pfeffer in 1897. They soon became part of the scientific English after translation of the Pfeffer's work by English-Australian botanist Alfred Ewart in 1900. A Google search at Scholar confirmed that mixotrophic has appeared in open scientific publication for more than 20,000 times. Thus, mixotrophic is standard scientific English term. All three terms, including mixotrophic, are used throughout the manual and in this presentation exclusively in their widely accepted and long-standing generic scientific sense. Moving into chapter 5, site selection and production system. Site selection, water availability, climate, waste disposal, local law, electricity, labor, market, technical support, and supplier. All of these are important when you are going to select the site where you are going to build your operation. It is true that if you are going to build your operation indoor, so you may need less to worry about the external climate, but again, adequate selection may save you a lot on energy, for example. Infrastructure, then namely building, reservoir, harvest basin, temperature control, culture tank, material that you will be using, characteristic, and the power backup. All of these are parameters that you need to look into and use to the best of your ability the component that will justify your investment. Aeration and water circulation. As mentioned earlier, the oxygen is driving force of the system along with the mixing. If you have oxygen and you do not have adequate mixing, you may result in catastrophic crop losses. So here in terms of aeration, water circulation, you can use air compressor, blower, pumps, air diffuser, airlift pump, venturi, A3 injector, oxygen, and other for oxygen, dissolved oxygen control. Now, another very important parameter in biofloc is the control of the solid. If you do not maintain adequate control, it can affect the system performance and can result in major catastrophe. So here we have different type of control method: settling, cyclone, drum, foam fractionator, scent filter, bit filter, among other. Now, the issue of feeding, here there are different type of device that you can use for delivery of the feed. And as you will see later, it is extremely important that the feed will be delivered in small quantity rather than in 1 or 2 or 3 times per day and then forget about it, because basically the feed between feeding can sit there and basically the quality is not going to improve over time. Safety system, you need to be aware of issues like theft, predator control, and of course, alarm system that will let you know if there is any problem that you need to come and take care of before you'll end up in a catastrophe. Now, for large operation, you will have a decent water quality laboratory. For other, you may get by with a small setup that will provide you the basic information for your water quality, because you need to know what's your alkalinity, you need to know the ammonia, nitrite, nitrate, all of these parameters, and not to mention total suspended solid, and these parameters that if you do not monitor and control them, again, you may end up with less optimal condition. Then moving into the recommended equipment, you will get a summary in the book what we have recommended. Now I want to go ahead and describe very briefly the two systems that we have used at our facility in Corpus Christi. The first one was a setup of 6 shallow, namely 0.45 meter deep EPDM lined raceway with a 40 cubic meter and 68.5 square meter raceway in a greenhouse with exhaust fan, dial-outs, alarm, and a shed cloth on the roof. Now, bear in mind that these raceways were built originally not for a nursery or grow out or anything along this line. We just had to use whatever we had and do the production trial in the setup. Each raceway has 2-inch sprayer pipe under a center partition with 18 2-inch airlift pump with 6.9 meter air diffuser, air blower that provided the air, and 1 2-horsepower pump with foam fractionator, settling tank, cyclone filter, and a venturi for air or oxygen supplies. In addition, we had 6 belt feeder and online DO monitoring, and around the perimeter of the system, we had netting to prevent the shrimp from jumping. This is especially true when you are dealing with the production of marketable size shrimp. As you can see here, the netting all around the structure to prevent shrimp from jumping. You can see here the center partition, at the bottom, the air diffuser. Here you see the airlift pump, which you can see them also here. And then you see the belt feeder. And here you see the pipe that sits under the center partition with the injector that basically when I'm running water through this pipe, and this water can go through the venturi, either with oxygen or with air enrichment, I can get steering action close to the bottom as well as oxygenation of the water. Here you see schematic drawing of settling tank. Here you see the venturi, which is not really very clear, the cyclone filter, the foam fractionator, and here is a device that basically helps with the dewatering of the particulate matter that you collect and then dry it, and you can use it as I explain later. Here you see an overview from the top of the setup where you see the center partition underneath the pipe with the injector underneath, and then you see the feeders, or the belt feeder and airlift pumps that all around, and the flow of water around the system, the center partition where all of the settling, foam fractionation, and other activity are done, including the venturi. All of these components are positioned outside the raceway. Moving into another system, this is the 1 meter deep in average depth, EPDM lined, as was the case earlier, 100 cubic meter, 100 square meter raceway, which were also under a greenhouse with exhaust fan, dial-out alarm, and a shed cloth on top of it. Each raceway has a perimeter netting, as was the case earlier, a center partition, 14 pump-driven A3 injector, 2 2-horsepower pumps, foam fractionators, settling tank, 6 belt feeder, and online DO monitoring device. A denitrification tank and concrete harvest basin also were provided to this setup. And what you see here, the perimeter netting all around. Here you see some of the belt feeder. Here you see the ropes that are holding the center partition. If you look at the top view, you see the center partition, you see the belt feeder, you see the injector that are positioned, unlike in the other raceway, on the perimeter, and they are designed to push water, deliver water close to the bottom of the raceway. Here you see a good picture of the injector, and here you should be able to see how it works. Basically, there is a pipe, 2-inch pipe, that delivers the water into the bottom of the injector. And while the water is running through the office here, it creates vacuum that takes air and mixes it with the water. And as a result, you get a very fine bubble that oxygenates the water and mix the water. Here, to the right of the injector, you see a settling tank, foam fractionator, the O monitoring probe that you see here, optical probe, and two horsepower pump positioned outside of the greenhouse. Of significance is the harvest basin that you see here with submergible fish pump that basically makes the harvest of the raceway basically very fast without any interruption. You can do it with a harvest of juvenile or adult or whatever you want. You can do it very easily. Here you see two outlets that basically feed the pumps, and this white pipe that you see at the center basically deliver the water into the harvest basin that you see here, that the fish pump can connect to it. Moving forward, chapter 6 deals with system treatment and preparation. Basically talks about prefiltration, disinfection, ionic and heavy metal composition. They need to find bacteria, whether or not you want to add it or in which form you can add it, and what are some of the sources that you can use to jumpstart the system. Issue of probiotic, Vibrio control, organic carbon supplementation. All of these are in terms of the system treatment and preparation. Moving into chapter 7, water quality management, namely mixing, monitoring, and control of dissolved oxygen in organic nitrogen species, pH, alkalinity, temperature, salinity, particulate matter, turbidity, waste product, trace element, heavy metal, use and sources of organic carbon. You will find a list of different organic carbon that you can use, and basically, as it's been published in other places, different sources, different organic sources can result in different characteristics of the biofloc that you have in your system. Transition from green to brown water, especially if you start with virgin water. Basically, you see here clear water. If you we started here with clear water, and then we shift into brown water, which is mixotrophic dominated water. Then we talked about the microalgae in the system. You do not want to have algal dominated system. You want to have biofloc dominated system, which has its own benefits. And then optimal water quality indicator for indoor biofloc dominated system. Chapter 8 deals with the nursery phase. I described the equipment, the infrastructure, tank preparation, broodstock, PL selection, PL transport, acclimation, evaluation, feed management, growth monitoring, survival, biomass estimate, juvenile, harvest and transfer, and routine tasks. All of these are important factors that can affect the outcome of your system. So you need to be very, very careful and follow the recommendation or be aware of them in order to avoid pitfall. Chapter 9 deals with the grow-out phase. Again, tank preparation, stocking consideration. Is there a limit to what you want to stock? Is it going to be 1,000, 3,000, 4,000? What are the criteria? What would you do, or what would you expect? And basically it translates into the system carrying capacity. If you overload it and you are not able to deal with the requirement of the system, you are bound to have a disaster in your hand. So feed selection, particle size, transport of the feed, storage of the feed, feeding practices, monitoring shrimp growth and FCR, shrimp evaluation, and routine tasks and the personnel that you may want to have for operating your grow-out system. Chapter 10 deals with the harvest, namely preparation, manual harvest of, you'll see some picture of the 40 cubic meter raceway, use of fish pump for harvest of the 100 cubic meter, live shipping and hauling, product handling, and cold storage. All of this is covered in chapter 10. Instead of talking much, I'd like to show you some of the pictures that are important in terms of their harvest. And here you see a good example of high quality shrimp being, after harvest, you move them immediately into a slurry of ice and water, and you will get this semi-translucent color of the shrimp, and instead of the whitish color. You have harvest basket if you are working on a small scale. If you have that, you may want to calibrate all of this basket to be at the same weight, so you don't need to tear it every time you go and weigh it, because basically you need to quantify how much shrimp you harvested. And here you see the way we've been harvesting the 40 cubic meter raceway by deep net, collecting them in a harvest fish basket, putting them on a hanging balance, weighing them after we let the water drip for a certain number of seconds, and then recording the information that we have obtained. We can also, instead of using the hanging balance, we can also use this type of device, that conveyor, that will transfer the harvest basket into this electronic balance that sit here. Here you see the conveyor. You weigh them, record them, and move them on. You can move them to slurry of ice and water, or you can move them into a harvest basin, a harvest bin, as you can see in this picture. Also, you can see the submergible fish pump that we have used with the external motor and the hydraulic reservoir that can be used. Nevertheless, there are other type of fish pump that can be worked from outside, and you connect only the hoses, and you do not need to put the fish pump inside your harvest basin. Here you see a picture of the water being taken from the raceway and moved by the white pipe into the top of a dewatering tower that drop the water back here, and the shrimp are coming back in and filling the basket so you can weigh them. Other option that you may consider, depending on what your needs, you can use cast net or traps to collect live shrimp if you want to transfer live shrimp to your client. And here at the bottom, you see three pictures. The center shows a spray bar that basically connected to a 12-volt pump that sucks the water from the bottom of the tank. You can see the tank on the left empty, on the right with water. It pumps the water that is enriched with oxygen, and it sprays it from the top. So this way you do not have shrimp sitting one on top of the other and suffocate. So moving into chapter 11, it deals with the waste treatment and disposal. Waste, basically wastewater and solid treatment option that you might consider, water and solid disposal option. These are very important factors that you need to take into account before you start production, because you cannot otherwise deal with it after you finish, when you don't have a work plan for how to go about disposing of the waste that you are generating. Now, for what you see to the left, you see wastewater solid, where you have ammonia that takes alkalinity, convert the ammonia to nitrite and then to nitrate. This is aerobic stage. Then you move to the anaerobic, no oxygen, where NO3 is converted into nitrogen gas, while phosphate is being consumed by the bacterial biomass, and then you gain alkalinity and pH. Now the water from the anaerobic can go into settler where you can separate the supernatant, get it back into your system, and remove the waste and dispose it off. On the right side, you can see a very crude method of drying the waste. Let it dry, you can grind it, use it as a fertilizer, or dispose it off your premises. We also used in our facility constructed wetland and with an emphasis on halophyte. As you can see on the bottom, these are a plant of Saliconia that can be used for feeding cattle as well as fish, shrimp, and other, especially if you are able to improve the quality or the percentage of protein in this plant. That can also, the seed can be used as a source for biofuel or for human consumption, oil human consumption. So just to show you some of the idea, and it is by no means the only option you might have, but to give you an idea what you can go about and how you can solve this type of problem. Moving into disease and biosecurity. Health monitoring, disease control, biosecurity, nutrition, probiotic, prebiotic, essential oil, vaccine, disease treatment, antibiotic, phage therapy, sample preparation and shipping. All of these are covered in this chapter, and what I show you here, only some of the issues that we have faced from time to time, including necrotizing bacteria. We had some problem with Vibrio, and we had other issues related to size variability, but not necessarily associated with disease, but in some cases, size variability being associated with the IHHN infection. Also wanted to mention the sample preparation, because I'll show you later also some other issue related to it, because if you have any issue with disease, you want to fix the moribund shrimp and put it in fixative and ship it to the disease diagnostic lab, and you want the sample to be processed or fixed at the right way so the lab can do the analysis. Otherwise, you will be wasting your time and your money, not to mention that, again, if you are shipping the sample to the lab, you need to be aware of hazard if you are moving material that can be of issue in terms of transportation, air transportation and other. Here, I wanted to show you a small section of a table that basically deals with the disease and biosecurity. I just cut part of the table and show it to you here. If we'll have the time, and if anyone interested, we can go into the electronic manual and I can show you how it works. But what you can see here, basically the observation, say for example, empty gut, then you see possible causes, you see underfeeding, inappropriate feed size, stress, namely poor water quality or disease. And then here on the right column, you see the blue page numbers. If you click on it in the electronic version, it will take you into these pages where more information is provided there. And with the Alt key to the left, you will go back into the place where you were. So it's very nice tool for navigation in the electronic form. If you are dealing with the printed material version, then you need to go and look for these pages manually. So just bear in mind that, again, you have this option, and it's nice to know that you can work with it. Moving into chapter 13, here we are dealing with economics of super intensive shrimp production system. This chapter covers important issue in terms of biofloc-dominated system, economic and feasibility. It provides an enterprise budgeting to evaluate economic feasibility, description and explanation of a bioeconomic model for business plan development, capital investment example for design, material, construction, and economies of scale, factor affecting cost of production and their impact on viability, economics analysis of the 2013 and 2014 trials at the Texas A&M AgriLife Research Mariculture Lab, and general marketing principle and sensitivity analysis. Now, the take-home messages, and again, as I said, there is no way in the world I can cover the economic aspect in this presentation, but some of the take-home messages are: biofloc-dominated systems are becoming less expensive with a better building material and economies of scale, namely lower cost per unit area of larger tank. Years of research have resulted in technically feasible biofloc system. Financial analysis demonstrate that viability depends on production scale and losses from diseases, mainly Vibrio. Mortality was the most important factor affecting the cost of production, net return, net present value, and the internal rate of return. Vibrio was the most important disease affecting production. Its control is priority in commercial production. High production cost and market price affect financial viability. Marketing is a deciding factor in selecting the best size at harvest, with niche market paying a higher premium for large shrimp. Now here you see comparison in production and projection from real data that we have obtained in terms of growth, survival, FCR, and other at 2011 and 2012. And basically, here you see the result were extrapolated for one greenhouse with 8 500 cubic meter grow-out raceway and 2 500 cubic meter nursery raceway. And what you see here, basically, what the estimated production per year, how many crops per year, production kilogram per year, production in metric ton per year, selling price. That's very important issue. You can plug in any number that will be reasonable for you, of course, depending on the other production parameter, to see how this will affect your analysis or economic viability. Now, total sales, variable cost, income above variable cost, fixed cost, total all of specified expenses, net return above all cost, payback period, net present value, and internal rate of return. You see some very, very high internal rate of return, and you say, this is too good to be true, and I would say you are right. Remember, this is just extrapolation. It needs to be, again, demonstrated day in, day out. As you will read in the book, you see that this is not a rosy path, and there are some issues that you need to deal with. And if you manage your system properly, you should be able to get very good results. Now, in the next few slides, I'll be dealing with research result, troubleshooting, appendices, which covers water quality procedure, microbial test, Vibrio monitoring, sample preparation, water quality lab and safety, water quality map, technical sheets, Excel file and form, and video. And finally, the index. So here we go. First, I want to describe a 62-day biofloc-dominated nursery trial in the 200 cubic meter raceway. There we used 90% chlorinated water with 10% nitrifier-rich seawater. We stocked 540 post-larvae, which were less than 1 milligram in average weight, with a coefficient of variation of almost 60%. Feed, we used the Easy Artemia and dry feed as well. In this particular case, because of the high size variability, we had to adjust the feed particle size and ration based on PL growth, PL size distribution, and assume survival and FCR. Feeding was done continuously with a belt feeder. We had the DO monitoring online, as I explained earlier. Alkalinity was adjusted twice a week using a bicarbonate. We use TCBS for Vibrio monitoring, the yellow and green colonies that was monitored twice a week. Nitrifying bacteria and sugar for ammonia and nitrite control. Remember, we are dealing with a nursery. probiotic for Vibrio control, settling tank, and foam fractionator for total suspended solid control, and the production was performed with no water exchange. Here is some water quality that's been monitored, and of significance is the fact that since we start early in the season and we didn't have temperature control, not active, we had temperature as low as 22.2, and in the afternoon, it got to 29.7 with an average of 26. Afternoon was, as you see here, early in the stocking, our temperature were low and later on increased. Salinity was down around the 30, dissolved oxygen, and pH that you see here along the line. You see the total ammonia nitrogen was a little bit about 2.7 milligram per liter, while nitrite was in the range of 5.5, 5.6, and total suspended solid. Moving into the Vibrio monitoring in this particular system, the green colony Vibrio, which is considered to be the bad guys, were maintained below 50 CFU per milliliter throughout the trial. Here you see total Vibrio that was increasing over time and basically got to 13,000 or so, while on the right graph you see the yellow colony and the green colony and how they fluctuated through the production cycle. On the bottom, you see the production that we have obtained in this particular nursery. We got 3.3 kilo and 3.4 kilo of shrimp per cubic meter, and with the shrimp that were 6.4 to 6.5 gram in average weight. Size variability, 11.9, 11.5 maximum, with a small one, 0.5 and 0.6. Coefficient of variation, remember at the beginning it was almost 60, now it dropped to 31, 36. Survival was very high in a range of 95 and 98, FCR below 1, and the amount of sugar that we have used, since you remember, we used clear water and we inoculated it with the nitrifying bacteria. Now, the summary of this particular trial: low temperature did not affect PL survival. Individual weight monitoring determined optimal feed size. Nitrifier-rich water prevented exposure of the post-larvae to high nitrite and ammonia. Probiotics suppressed green colony forming Vibrio. TCBS, agar plate were good for monitoring pathogenic Vibrio. We used the A3 injector, and at the beginning we were not sure whether or not we can use them with a very young post-larvae, and we realized that we can use them without affecting or damaging the post-larvae. We also found that 1 2 horsepower pump maintained dissolved oxygen above 4.4 milligram per liter with biomass load of 3.43 kilogram per cubic meter with no oxygen supplementation. I should mention that recently there are suggestions that you may want to keep the dissolved oxygen in your system above 4.4. In our particular case, although we got very good result, and if we needed, we could switch the second pump, and certainly we could have reached the 5.5 milligram per liter without too much of a trouble. Moving into the 640 cubic meter raceway, where we did also nursery, water preparation, DO monitoring, Vibrio monitoring and control, and use of probiotic and alkalinity adjustment were as specified for the previous nursery. We stocked this time 675 post-larvae of the same size in per cubic meter. We use the same settling tank and foam fractionator tools, but in addition, we use also the cyclone filter that you can see it on the right side, which was also connected to the pump, so we could get also additional particulate removal while the pump was running. We feed with a belt feeder. At the beginning, we wanted to try to evaluate the impact of easy artemia plus dry feed compared to dry feed only, and later on we realized that basically we need to switch to easy artemia plus dry feed because we found quite a few PL with empty guts, and thus we did not continue with the comparison. Now, particle size and ration were based on growth, PL size distribution, and estimated survival and FCR. Water temperature, DO, salinity, and pH were similar to what we experienced in the 100 cubic meter raceway, and the trial was conducted again with no water exchange. Some of the water quality, total ammonia nitrogen, similar to what we saw earlier, nitrite, total suspended solid, and alkalinity. Moving into the conclusion, basically slight increase in stocking density resulted in performance like in the 100 cubic meter raceway for ammonia, nitrite, alkalinity, TSS, and VBO control. Use of easy artemia in the first few days after stocking minimized the number of PL with empty guts. Shrimp performance was slightly inferior in terms of survival, growth, and FCR, and coefficient of variation compared to a 100 cubic meter raceway. Now, unlike the 100 cubic meter raceway, oxygen was required for control of dissolved oxygen in the culture medium. And what you see here, we got 3.1 to 3.22 kilogram per cubic meter. Animals were a little bit smaller, 5.5 to 5.7 gram average weight, maximum size 12.4 to 11.8, and the minimum was similar to what we had in the 100 cubic meter. Coefficient of variation was a little bit higher than what we had in the 100 cubic meter. Survival slightly lower, FCR also low, below 1, and the amount of sugar was similar. Now, raceway field with what now we are moving into the grow-out phase in the 100 cubic meter raceway. We filled the raceway with 75 cubic meter of natural seawater, and this time we used 25 cubic meter of biofloc-rich water, which we took from the nursery tank, and we filled the raceway. And you'll see the drastic impact of this biofloc-rich water on nitrogen species. Stocking was this time 500 animals per cubic meter of 3.6 gram in size. We used 35% good protein diet that was produced by Ziegler. Ration were adjusted based on estimated growth, survival, and FCR. This is very important tool that if we'll have time, we can talk about it a little bit more, because otherwise, how would you determine how much you feed your shrimp and not overload the system and not starve your system? That's very important management practices that you need to, or you may want to review when you are reading the manual. Feed was delivered 24/7 with a belt feeder. TSS control and DO monitoring were similar to what we use in the nursery, and we use also alkalinity control. What you see here, that basically the morning and afternoon temperature were much higher than what we experienced in the earlier nursery production trial. Salinity were as low as 25.4 and up to 34.7, dissolved oxygen and pH. You note that here we have 6.2 and 6.6 as a low pH, and certainly you may want to watch for pH drop, especially when you are dealing with a high biomass. Now, what we found that basically nitrifier-rich water accelerated development of a highly efficient mixotrophic system that maintained low total ammonia nitrogen, nitrite, using organic carbon that came only from the feed. Unlike in the nursery where we added sugar, here we did not add a drop of sugar and still managed to get very low level of ammonia and nitrite. Nitrate increased from 67 to about 310 milligram per liter, average TSS and settled solid to 90 and 12 milliliter per liter, and the 2 horsepower pump per raceway and 14, the A3 injector supported oxygen demand of 9.2 kilogram per cubic meter of shrimp biomass. This is to say that if you are going to try to use this system, by no means, I do not recommend that immediately you shoot for this high biomass. You may want to practice first with lower biomass, and then you increase the biomass as you get familiar with the system and is able to maintain it and control it. What you see as a result of this particular trial, we had an average yield of over 9 kilo per cubic meter. The average weight of the animals above 22.7, survival in the range of about 80%, FCR 1.48, and growth per week 2.13 and 2.12. Now remember, right now there are strain of shrimp that is capable of growing much, much faster. And in this particular case, you may want to adjust your feed accordingly to accommodate the high growth of the animals so they won't be underfed. Moving into the grower trial in 640 cubic meter raceway. Each raceway was filled with 22 cubic meter natural seawater and 18 nitrifier rich water. We stocked the same density of 500 animals per cubic meter, 2.66 gram average weight. We use the settling tank and foam fractionator for TSS control. We use the YSIDO monitoring system. We control the total suspended solid and alkalinity as well as pH. Feeding continues with the belt feeder, and ration were adjusted based on estimated growth, survival, and FCR. And the feed that we used were two types of feed. 3 raceway were fed the HI35 with a cost at that time of $1.75 per kilogram, and the SI semi-intensive 35, the same level of protein, which cost $0.99 per kilo. Here you see basically the result, summary of the result. Nitrifier rich water kept total ammonia, nitrogen, and nitrite low, basically below 0.5 and below 1.22 milligram per liter. This is as compared to the nursery where we had much higher value. Nitrate increased from 40 to 360 milligram per liter. Bottle oxygen was required to support the shrimp biomass, unlike the situation in a 100 cubic meter raceway. You see the temperature, summary of the temperature, salinity, DO, and pH. Now, TSS control, one thing that you may want to bear in mind that basically the hyperintensive 35, we use the foam fractionator much less time, as well as the settling tank, as compared to the SI35, which you see the differences, 812 compared to 1253, 87 hours compared to 391. Summary of the information: final weight 22.12 gram average weight as compared to 19.7 in the SI35. The growth 2.03 with a hyperintensive as compared to 1.76. Biomass was higher in the hyperintensive. Yield 9.74 as compared to 8.71. FCR of the hyperintensive 1.25 as compared to 1.43, and survival 87 and 88 in the two raceway. Moving into troubleshooting, and here I want to show you basically troubleshooting in chapter 15. Again, we have a very extensive table summarizing different problems that you may encounter, and it suggests what you want to do in order to resolve it and how you go into certain page indicator and read more about the issue. So on the left, you see the problem, and in this particular case, water quality, low alkalinity, what possible causes, solution, and then additional information if you click on the page number on the right column. So as I said, this is only a small example of the extensive table that is provided in chapter 15. Moving into the manual appendices, where here we have water quality procedure, where we describe the O, pH, temperature, salinity, alkalinity, total ammonia, nitrogen, nitrite, nitrate, soluble solid, TSS, phosphate, turbidity, and chloride monitoring the way we did it, and some other product available on the market. But by no means we are trying to cover all of the test kit and the procedure that are available, just to give the reader some of the tools available and what we have used and what we found. Also, we go into the microbial test, where we describe Vibrio monitoring and how to identify them. We describe also the preparation and the seeding of the TCBS plate. Basically, we provided a video that instruct people which are not familiar with it, how this can be done. And certainly it can be very useful for those of you which are not familiar with the procedure. Sample preparation and shipping, how to prepare a sample if you are going to preserve it in Davidson fixative, how you need to cut the tissue in the cuticle in order for the fixative to penetrate the tissue, so you can get a very stable tissue that can be processed by the disease histology lab. Moving into the water quality lab and safety issue, suggested equipment and basic lab safety. Now moving into the water quality map, and here I want to show you, this is basically interactive water quality map that quickly perform routine and special water quality calculation. It hides the chemical and the math detail behind visual interface, and like Google Maps for aquaculture. Basically, you see here the alkalinity in milli-equivalent per kilogram, here alkalinity milligram ppm, and you see the different line of the pH. And what nice about it, basically it tells you here where is a dangerous area that you do not want to be in terms of the ammonia, and here in terms of the carbon. And here you see different parameters based on your water quality that you can plug in and see what can happen. And I'll explain a little bit more how this software is working, and I will encourage you to read a little bit more. Here, for example, you remember earlier the green zone, and here you see, for example, you have pH, alkalinity, ionized ammonia, CO2, calcium, omega, hydrogen, aragonite, and calcium, and magnesium, calcium, and sodium to potassium. Here you see where you are standing here, and what's the pH, alkalinity, unionized ammonia, and CO2. And while here you are not where you want to be, here 7.5, 1.8 alkalinity, 3.2, and 2.38. And here it tells you basically what are the type of chemical that you can use in order to get into the optimal area that is here, and where you have the aragonite of above 1, which is the safe for you to be here. So it tells you that you can take the bicarbonate and sodium hydroxide and the quantity that you need to add. This is assuming 100 cubic meter raceway at a 25 Celsius degree and salinity of 30 parts per thousand. So just imagine that you have here a list of another 13 combination that you can use if you want to do that. So it gives you that, so you can see that you can ensure correct CO2 and unionized ammonia level, easily manage calcite saturation state, easily target optimal nitrifier zone, and clear direction for adjusting water quality. So you do not need to do all of the calculation. You just drag this to here, and it will tell you what you need to add to the water. And you have noticed later on we talk about this KCl, potassium chloride, and why it was added in order to maintain the ionic composition of the water. Here you see basically a situation where the start point is here, where you have 7.1 pH, alkalinity of 1.65, unionized ammonia 1.27, and 5.72 CO2. And then you see here predicted post-feeding after you feed, after 7 hours, what will happen to the selected water quality that are imported: pH, alkalinity, ionized ammonia, CO2, all of this are listed. And then what you need to do, just to drag it here, and it will tell you what you need to add to the water in order to prevent inadequate water quality for the shrimp to perform in your system. So basically you want to be in the green zone, and it shows you how you can go about it. And as I mentioned, here's just one example of what you can use, but you can use different other combination that will get you there. As you can see here, different type that can be added. And here again, after 4 hours, what you can expect in terms of the changes in water quality, and you move it from here to here. And what you will have to add, you want to add the bicarbonate and sodium hydroxide, fine. If you want other component, you have it listed. So that's what I wanted to show you here. And another thing that is very important, as I mentioned, the ionic ratio of certain anion and cation in your water. And basically this slide shows you what can be done in order to adjust the ionic strength and ratio based on the original requirement that I showed you earlier in the introduction of natural seawater and the artificial seawater. So it gives you and tells you how much you need to add of each component in order to maintain the ratio that you were targeting in terms of magnesium, calcium, and sodium and chloride ratio. Now here you see another example of how you can drag your set point into the green zone. Either it is in terms of critical unionized ammonia or percentage unionized ammonia. As you know, the percentage unionized ammonia will vary based on pH, temperature, and salinity. And again, you do not need to do the calculation. You just drag it there and it will show you what and where you are and whether or not you have still enough room to grow and not worry from reaching critical value either for ammonia or pH that can affect, negatively affect the shrimp. Moving into the technical sheets, there you have conversion, friction losses, periodic table, volume calculation, and more. And then we move into the Excel sheets and form. Here, there is a table with different Excel sheets and form. And when you click on the electronic version on the page number, it will take you to the form. If you click on the Excel sheets, it will take you to the Excel sheets and explain you and show you different factions that can be done by the Excel sheets. And if we have time, we can glance through some of the Excel sheets and what you can expect from these electronic sheets that were provided. The same is true for the video. We have large number of video, 32, that you can click on, and it tells you also here where it was mentioned, what you can see here, and it gives you a more detailed description of what is done and how it's been done. So if you are interested, you will be able to review it. Moving along to the index, similar to what you saw in the other tables, basically I just took part of the index. It's very extensive, and as you can see, for example, under the A, acclimation, you have acclimation and feeding, acclimation low salinity, observation, blah, 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 blah. Everything is listed here. You click on it, you go there, and you get more information. Note that some of the numbers are also, you have accompanied with a letter T or F. T, it means that you have also a table that tells you more about this whole issue, and F is figure, which gives you a picture of the information. And I believe by that, we got to the end of my presentation, and I suggest we'll take 5-minute break, and then I'll be glad to take any question from you guys if you have any. Mr. Lim, what do you think?
Yes, we'll take a break. We go to the loo, the toilet, and come back. And then we'll answer the question. Yeah, answer the question and answer session. Yeah.
Excellent.
Retired Regents Fellow Professor with Texas A&M AgriLife Research. After obtaining his Ph.D. from Tel Aviv University, Israel, he joined National Center for Mariculture in Eilat, Israel, where he served as head. So you're ready, Tzachi?
I think I'm ready. Let me see.
Yeah, the four questions in the Q&A. Yeah.
Let me just bring the screen back.
Yeah.
You know, where is it? Let me close everything here, and I need to return to meeting. Okay. It doesn't let me get there. Let me see. Okay, now I can see you, and we need to share screen, I guess, and share. And it will be, let's see here, I want to take this, and okay, now I don't see yet the screen. Do you see my screen? I don't see anything yet. Oh, okay, here, now, where is it? Okay, share. Okay, host disable participant screen sharing. Okay, so where do we start?
So we start with
can you see my screen or not yet?
No more screen.
Okay.
No more screen. Now we are.
Do you see my screen or you don't see my screen?
I don't see a screen anymore.
You do or not?
No.
Okay, let me see. Okay,
you want to show the screen?
No, I can see you. I can see you, but I click on share screen, and I see this, and I see you, but let me see. Hold on.
You want to share screen? You can share.
Yeah, I click on share, and I see myself here. You know, I may need to log in again, try to do that, or return to meeting. I'm clicking on return to meeting. And here I have question and answer or whatever, but I still do not see my screen here, which I wonder why. Let me see.
No, you can share screen. No problem.
Let's see, chat, record, disable, hide, no, hide, share computer, sound, optimize. What do you see on your screen right now? Nothing?
The screen, that's the Zoom zone. I can see Zoom phone, you know, that's the Zoom screen.
Uh-huh. I can see myself, I can see you, but I cannot see
no, you can
my...
see your, no, you click too fast.
The what?
You go back to your...
Can you see now my screen or not?
Can I can see your screen, but there's nothing on. Yeah, now I can see your screen. Now we can...
Now, can you see my screen or not?
Yeah, can.
If you don't, you see it or not?
Yep.
My screen?
Yes.
If you don't see it, yes, you see or you don't?
I saw your screen. The manual index.
Okay, so you see the index, right?
Yep, yep.
Okay, so we can start. Very good.
Okay. So we start with the first question from Michael Barnes. What are the simplest SOP using the minimum WQ parameters to maintain a stable mixotrophic balance on a practical daily routine within the system? That is the first question.
Let me see if I can
you
read the question here.
Yeah, you click the question and answer, you can see.
What are the simplest SOP using minimum water quality parameter to maintain a stable microscopic balance on the practical daily routine within the system? Okay, so basically the question is, how would you build and maintain a mixotrophic system? So here we need to divide it into two sections. If you are working with virgin water, you need to build the mixotrophic system from the ground up, because at the beginning, you have a very limited amount of nitrifying bacteria. And if you can enrich the water with nitrifying bacteria, it will start developing and get to the stage where it can handle the 2/3 of the ammonia that basically you want it to metabolize, while only 1/3 of the ammonia is being taken by the heterotrophic bacteria. So you need to do it gradually, as at the beginning you don't have many nitrifier in your system, and that's the reason why you need to add quite a lot of organic carbon in addition to the amount of carbon that comes with the feed. And your target is to reduce the amount of carbon that you add to the system. And we have in the manual step-by-step procedure how to get there in order to get to the stable nitrifying mixotrophic stable environment where the nitrifying bacteria is capable of handling the 2/3 of the ammonia. Now, once you get to this stable state, what you need to do is to monitor the alkalinity and pH, and you can monitor the ammonia, nitrite, and nitrate, and see where you stand, whether or not in terms of the system, if it metabolizes the ammonia properly, and the nitrite, you need to see drop in alkalinity, drop in pH, and you need to run the adjustment. You run also test for the total suspended solid and make sure that it is not going above certain level. We recommend 350 milligram per liter, and some people will go and look into the settleable solid, looking into Imhoff cone, which I really do not prefer, and determine based on the settling cone reading and adjust the control of the particulate matter in the system. These are basically the indicator that you need to be aware of. And of course, based on the amount of feed that you feed, whether or not you have overfeeding, and when you sample the shrimp, you want to make sure that the shrimp are performing according to your expectation in terms of growth, FCR, and other parameters that are important for your system management. Did I manage to answer your question?
Michael, it's okay with you? And
Okay.
Tzachi, answer your questions. Okay, we go back to the next question by Dr. Shahabuddin. He said nursery production seems very low at 3.2 kilo per cubic meter. How we control if pH is higher than 8.5?
Okay. The 3.2 kilogram per cubic meter, you need to remember that in our system, we basically was using the nursery, the same tank for nursery and for grow out. So if we were to go with a maximum sustainable biomass load with the nursery, we would have continued, but we wanted also to run the grow out. So we had to harvest the nursery tank and restock them. So that's adds also stress to the shrimp in order to restart the trial. In a real world, you transfer the animals from the nursery directly into the grow-out tank, and without concentrating them in one tank as we used to do and then splitting them, because it's a lot of damage that can be inflicted on the animals. So that's one portion of your question. In terms of the the high ammonia, high pH, basically it depends also on the size of your tank. For example, I'll give you a good example. When we start to work with the system, and we had at the beginning more algae in the system than what we wanted, and it was photosynthesis that was generating very high pH. Basically, we got a pH of 9.8. You can imagine what we did in this particular case. We just injected CO2 into the system for several minutes, lower the pH, and then it stabilized the system. Now, the beauty of the water quality map, that you can go there and also play with this map, and it will tell you what you need to do or what you can do in order to bring it down. So hopefully this gives you some indication of how to go about it.
Next question by Michael is, let me clarify, what are the minimum WQ parameters that need to be measured, and what daily frequency, and how often to add required chemical balancing agents as indicated?
Now, yeah, one of the things that we have used, and we used it also to a certain extent in certain commercial hatchery in, I would say in the Americas, if I can dare saying, or including, because I saw it also implemented in several large commercial scale hatchery where they try to screen the post larvae starting for 4 milligram size and removing the small one and perhaps doing second screening to reduce the size variability. Ideally, you want to work with 5. If you don't have much choice, you will work with 10 or whatever you have, but that's what you may want to target, as it will improve the performance. That's for this issue. Now, I see here to project total suspended solid and floc level in similar to the water quality. I'm not so sure I fully understand the question.
It's from Mark Rowell. Maybe he can.
Is there any model being used to project total suspended solid? Basically, in our system, after we learned how to operate it, we knew how often we need to monitor the total suspended solid and make sure that we are within the parameter, but we didn't use any model. I should say also that when you monitor the total suspended solid, you need to make sure that the method that you are using is accurate. I had an incident where I have given a total suspended solid erroneous information, and based on this, we were operating the settling tank and the foam fractionator, and we lower the concentration below certain levels. Say, for example, if you go below 100 milligram per liter, basically the number or the quantity of the nitrifying bacteria, because their number is much, much lower and their multiplication rate is much, much slower than the heterotrophic bacteria, we had to add a little bit of carbon to enhance the heterotrophic bacteria until the nitrifying bacteria recovered. So that's something that you need to be aware of and not overshoot in terms of stripping or let the total suspended solid get out of hand.
Okay, the next question by Min Tuya. She said that she's constructing a 25.
Yeah, I mean, I would.
So you can.
I would suggest, strongly recommend that you purchase the manual, and basically that's the place to say that if you are interested, I strongly recommend that you buy the electronic version and the printed version from Elsevier. I saw that they provide a 50% discount if you buy the two books, and basically instead of 150 for the printed version, you pay only 50%, and then on the electronic version, again, 50%, and for 150 altogether, you get the two of them, and it will be much, much useful information that you can see the details of what we have used. Of course, in terms of the material, you'll see what we use, but you can use anything else that is available at your place, whether or not you use concrete, whether or not you use HDPE or high density polyethylene, whatever is cost effective at your place, you can build it. One thing that you will notice that circulation and suspension of the particulate matter are very important. So ideally, you do not want to have a corner where particulate matter can accumulate, because then you have a trap that will generate H2S that can affect the system performance and the shrimp.
The question by Fabio is interesting, so I think it's better for you to read. It's a very long question. He's talking about ORP monitoring.
Okay.
Yes. Fabio used to teach
about I'm glad
ORP.
that you basically, okay. I'm reading your question, okay? Yeah, basically, I agree with you in terms of the people that really do not know how to manage BFD claim that they know, and they take people for a free ride and then leave them high and dry. In terms of your suggestion using of ORP, certainly you can use it. Anything that you learn that you can implement, that will be beautiful, because basically in our system, when we're feeding with the a belt feeder, for example, you just not dump the feed on the belt feeder and walk away and that's it. You know exactly that before molting, the shrimp won't consume the feed. And this will be predicted also based on the dissolved oxygen, ORP, and so on and so forth. And you can adjust accordingly, stop feeding until they molt, and then go ahead and continue. And what we mentioned, the issue of predicted growth, survival, and FCR, it's a useful information that can serve as a guideline. But if you have other tools that can be incorporated or replace this prediction, welcome, why not? I mean, that's the beauty of learning from each other, absolutely. Okay, yeah, I really hope the reason why we developed this manual, because we saw too many, we call them shrimp shyster, those people that will sell something that they don't have. And the producer is the one that paying the price. At the beginning, when we published the book with WAS, our thought were to give the book free of charge. But then people say, if you get something free, you won't be able to appreciate it. And we went for the other option. Unfortunately, because of different issue related to the word mixotrophic that I have explained in my presentation, WAS was not able or not willing to provide the, to sell the book anymore. And we had to go and publish the book by Elsevier, which resulted in 2-year delay in publication, which was a real shame, but that's the way it is. There is nothing we can do about it. The bottom line, hopefully people for fraction of what they are going to invest in their operation will be willing to buy this manual, read it very carefully, and learn from it before they are going to dig in the ground and proceed from there.
Okay. Any more questions from the floor? I don't see any more questions. Gilbert Pang say, where can I download this presentation? They are already answered. We will give the Tzachi presentations to all the registrants. I will send the presentation after the seminar. But regarding the menu, you have to buy from Elsevier.
Wonderful. Thank you very much, guys. And if you have any question, just let me know.
Any more questions? We still have time. We still have time, about 15 minutes or so.
Okay. Thank you very much. Take care.
I don't think any more questions coming. There's one question from Victor. He asks us the Andrew J publication compared with clear water versus biofloc farming system. They indicate better results from clear water system and better FCR. Better survival.
Say it again. What was the question?
He said there's an article there's an article in 2017 study by Andrew Ray, where he compared with the clear water versus biofloc shrimp farming system.
Right. Okay. You see, biofloc system is easy to manage, but you need to learn. Once you learn how to manage it and you have good seed stock, adequate management in place, you will get very good result. As I had demonstrated in my system, you can get over 9 kilo of shrimp with a very low FCR and other. So if you compare apple to apple, you see that biofloc is better. But if you want to be on the safe side and you want to take precaution and you can compromise on growth and whatever, then you can go with a hybrid that will filter particulate matter and other. Remember, the bottom line is how you manage the particulate matter, oxygen, and the health of the animals. So if you manage to come to a more cost-effective way to do it, fine. I'm not telling you you have to do this or other. I presented one venue that we have used with a very good result. And I also, in my book, if you read it, there were some issues, so there were some problems. So you need to be fully aware of them. It's not all is working. So be aware of it, and then you decide the way that you want to design and operate your system.
Okay, I have a question for you, Tzachi. You have your high intensity
I see here
system. Then how do you take away the molting shell? You know, there will be a lot of molting shell in each molting cycle. So do you discharge it or you just leave it in the system?
Okay. Are we asking about removing of the shell, the mold?
Yeah, the molds, yes.
Okay. There are devices that can be used to automatically remove the shell from the water. What we use in our system, in 100 cubic meter or so, we used to, when we had a wave of molds, we collected them from the surface and removed them this way. But there are devices that based on airlift pumps that can concentrate the mold, and then you can remove it along with any weak or moribund animals. So that can be done. Now I see here a question. Do you prefer open air tank or closed shade system for biofloc? My preference is to have contribution from natural productivity, namely the light, natural light. I do not want very high light intensity, but I do want to see some microalgae in my system. In some of our study, and we published it, you would like to see more diatom in the water, which benefit the shrimp, which in artificial light or inside the building, you won't be able to see generally. That's basically the issue that I want to mention. Now, there is another question here. What's the important criteria in increasing harvest density? You need to know what's your carrying capacity of the system. If your system carrying capacity, say, is 10 kilogram per cubic meter, as an example, and you want to harvest 1 gram animals, your stocking density will be, at the end, 1,000 animals per cubic meter. 1,000 or 10,000, let me see. 10 cubic meter, if you want 10 kilo, it's 10,000. So you stock 10,000 animals. So based on your system carrying capacity, you design your system. That's very, very important that you make sure that your system is capable of handling the water quality, including dissolved oxygen and other, to maintain the biomass that you want. Someone else asked about the belt feeder. If you run any search on belt feeder, or you look at the information in the book, you will be able to find them. I think the Chinese have a knockdown model. I never tried them. I don't know what's the quality, but Germany is producing very good quality, and there are others. So you may want to evaluate your option before you settle for one. There is another question here. What are the precautions we have to take while shifting the shrimp from nursery to the grow-out, and what the best method to shift them? Okay, very good question. I showed you, first of all, the fish pump. Ideally, you want to plug in the fish pump and pump the shrimp to wherever you want. You can pump it. It's been demonstrated for 3 kilometers without any problem. So that's one thing that you can do. If you don't have a fish pump, again, collecting the shrimp in small quantity and move them, you do not need necessarily to put them in well-oxygenated water. Depending the distance you need to transfer them, you can transfer them wet into the tank that you want. So different ways that you can do it. Make sure that you are not expose them to high temperature, and you should be okay. So these are the kind of precaution that you need to take into account. Now, bear in mind that if you want to be fancy and you have the money, you can also quantify and count the shrimp as you pump them from your nursery into the grow-out tank. So that's another device that can be plugged into the fish pump and count the shrimp and tell you exactly how many animals been transferred into the grow-out tank.
Okay, there's one, organic carbon supplementation. Would the system be considered biofloc or essentially just growing shrimp in areas?
What was the question, sorry?
Without organic carbon supplementation, would the system be considered biofloc or essentially just growing shrimp in areas?
Yeah, I mean, that's the beauty of the mixotrophic system. If you are asking about mixotrophic system, there we did not add any carbon. Once the system is stabilized, the only carbon, organic carbon that goes into the system is from the feed. Now, if you are dealing with a clean water, it's totally different story. There, once you feed, you need to remove the particulate matter or underwater through a biofilter, sterilize the water, control the water, temperature, oxygen, oxygenate the water, disinfect the water, and bring it back into the system. So that's a different approach. And I'm talking about the biofloc. And if you are talking biofloc, my preference is the mixotrophic system where no carbon need to be added beside the amount that comes with the feed.
Okay, the next one, we come from a shrimp farmer in Singapore. How can we know that we have completely removed the dead molted shrimps which is laid at the bottom of the big pot? How do you remove all the shells of the shrimp? This one, deboxing.
That's a different issue, and in tanks like, say, 700 cubic meter, scooping the bottom might be your best option. And again, the best thing is to maintain adequate management practice that will minimize mortality. And then if you get to this stabilization, your mortality will be very, very low. But it's not easy to estimate. And what you may want to do, again, in our calculation of the daily ration, we estimate certain survival, FCR, and growth. And based on these estimates, we adjust our ration. So if you know, for example, that you experience 0.5% mortality per week, you adjust your feeding accordingly. So instead of 100 animals in the first week, in the second week, you will have 100 animals minus 0.5%. And this is the way you continue. So that's the best thing I can tell you, because if you find that your survival at the end of the nursery or at the end of grow out is, say, 80%, so you take the period and you say, over this period, I lost 20%, so my weekly losses are so-and-so, and you adjust your ration. And instead of collecting the dead, you can scoop the bottom from time to time and see if you can pick up any dead. If you don't have any disease, the number of dead shrimp that you will be collecting will be very, very small. If you have disease, then it will be much more complicated to collect all of the dead and estimate what was your mortality. So the prevention is better than dealing with mortality associated with diseases.
Okay, don't your system have a shrimp toilet that they will take care of the discharge, like the molten shells, if it's too much? Or you just leave it in your system and let it, and let the shrimps eat? Where does the shell decompose in the system, in your system?
Yeah, I mean, the shrimp, as you will notice at the beginning, say up to about 10 grams, you will barely see any mold floating on the surface, and the shrimp will consume it. As they grow to 12, 15 grams or so, then you may see some mold floating, and then you can remove it. But before that, generally, you don't have to deal with a collection of the mold.
So when they're bigger, then you can see the more shells. Okay. So, but if you have density like 10 kilo per cubic meter, I'm sure you can see a lot of shells during molting, because banana normally can molt 2 times or 3 times a month. You know? So you have
and not only that,
a lot of shells.
Yeah. Okay. Yeah, exactly. The issue of the mold that you can collect very clean mold that there is an industry that developed on the use of chitin that if you are large enough and produce enough mold, then it will be another side stream of income.
Okay, so if you can give us where to buy the equipment, I think Beboxing will be interested.
Sure. Okay.
So the next question is from Bangladesh, Dr. Sahabuddin. He's interested to make collaboration. He's also working on BFT in Bangladesh. So maybe you can answer this question.
Sure. As a matter of fact, we tried to work with a group in Bangladesh, and they contacted the two of us, as I remember, but basically at one point it stopped. So I don't know. I will be more than glad to do that.
Basically, it's just funding, you know. It's a lot of things that.
Exactly. Exactly.
If there's no funding, it's very difficult for Tzachi to come out with finance, because I don't think he's capable of financing. So it's more on the brain work, and the country has to come up with the funding if they want to have a serious collaboration.
I know that there is an investor in Bangladesh that right now working with Ituba shrimp, basically where they have 8 of our raceway working in biofloc-dominated system, and they were discussing developing similar system in Bangladesh. I don't know where it stands right now, but I know that they were talking, and whether or not it will materialize, it's yet to be seen. So that's what I can tell you, but I'll be more than glad to work with you. And as Mr. Lim said, funding is a major issue.
Okay, there's one question from Yapli. What are the potential sources which cause empty gut in the PL in the nursery stage?
Say it again. What was the question?
What is the potential sources? What are the potential causes of empty gut PL in the nursery stage? At the nursery stage, it's inside the chat line from Vietnam.
Okay. The cost of post larvae. That was a question.
Yeah, during the nursery cycle, yes, correct.
Yeah, but I know that up until the last few years, PL supply were a major issue, quality and supply. Now we have quite a few suppliers, including the CP that built a hatchery that is claiming to have a very high quality post larvae that are capable of growing at very fast rate. So there are several of them, and the cost associated with it, it used to be in the range of $7.5 a thousand. I don't know what's the current price, probably lower. And that's where we had it here. Remember that in the US, for the most part, most of the production, and which is not really much, is done in outdoor pond and not necessarily in closed recirculating system. So for the hatchery to operate only part of the year, it is very expensive, unlike in other area where the production of post larvae is year round, and they can afford lowering the cost of post larvae to $1, $1.50, or even lower per thousand. So that's some of the factors that need to be taken into account.
Okay, I have a question for you. Is it better to buy PL 6 and 7 into your system, or buy a bigger PL like PL 12 to 15?
It depends on the distance where you need to move them. The stronger, the larger the PL, the stronger they be. Although we do not have any problem working with very young PL, PL5, PL7, you can work with them. but again, it's a question of the quality of the post larvae, because if you have PL5, which with an average weight of say below 1 milligram, and you have PL5 of say 3 milligram, for example, it shows that the latter is being produced under much more optimal condition, and you get stronger post larvae. So for that reason, you will see producer settling for certain hatchery that known to provide higher quality post larvae, and that's very, very important.
Okay, when you buy a smaller PL, is it necessary that you need to build zooplankton in your system, because small PL, like say, maybe cannot take your powdered feed? Yeah.
We did the trial in which we tried to feed the shrimp the easy Artemia plus dry feed as compared to only dry feed. We found that the easy Artemia was very important, but for the most part, again, if you have a natural productivity like the aqua mimicry or other method of improving the natural productivity, it will certainly benefit the shrimp, especially when they are young. So anything that can enhance the natural productivity should be of a benefit in this particular case. Now, I should say also, when you look into the production of the post larvae in the hatchery, there is a possibility to grow the post larvae without algae and using only artificial feed. But the bottom line is what will be the end product, the size of the animals and the vigor of the animals. So if you can produce good quality, good luck. If not, I'm in favor of using algae and even other zooplankton as supplement, not necessarily live Artemia, but something comparable will be of benefit.
So there's one question there from Mr. Rao. During the nursery as well as grow up in indoor culture, some shrimps appear to be bluish color. What's the reason for that?
Yeah, that's something that you find when the animals are being grown indoor for the most part. And if you will have the light, natural light, generally you will have much less of this problem. It can be overcome with some supplementation, feed supplementation, supplement that can overcome it and make the shrimp look more natural, I would say.
Because they are short of some minerals, blue syndrome, we call it in the shrimp.
I don't know if it's the blue syndrome, the disease you are referring to, or just the color, which is bluish. My experience, when you grow them indoor, you will get bluish color.
Okay, but if you, in China, if we get bluish color, we get the buyer will not buy because they will not buy.
Okay.
Yes, yes.
So this certainly need to be addressed, and there are different ways that you can do that. Yes.
Probably we feed them with some acetacin or some other algae. They can
Exactly.
Yes. Can improve the color, spirulina or something like that. I think they're probably short of carotenoid, so probably some minerals like this can help the bluish color.
Absolutely, yes.
Okay, can mixed trophic system be used in outdoor or only in indoor system, indoor farm?
When you have a biofloc, and if you maintain adequate concentration of the biofloc in your water, namely do not go below a certain level, because if you go below a certain level, again, the biofloc cannot metabolize the ammonia. Then either you need to start supporting the heterotrophic, that they will take care of the ammonia until the nitrifying bacteria will be able to overcome, or it can result in transformation from biofloc-dominated into a green water. So this is a balance that you need to work on. And if you maintain adequate concentration of the particulate matter, you can do it also outdoor, no problem. But it requires adequate monitoring and control. Because if you do not have adequate concentration, light penetration is higher, and algae, microalgae will start developing in large quantity. You will have algal bloom.
I think the trend now, even in China, the trend now is going for indoor system for in the greenhouse and a smaller pond area. This is a trend now in China.
Yep.
They also find it difficult to grow in outdoor pond because of the climatic condition. Climatic change is very disaster. So now they are promoting indoor system with smaller cubic.
Okay.
Yeah. Okay. Any more questions? Oh, we already we'll give it another 5 minutes before we close. It's 11:05. We already run out of time. Yeah. No more questions. I would like to close the session. And if you have any more questions, you can email to Tzachi Samocha. I will send all the slides to all the participants, and you can take it from there. And I will be putting the presentations on YouTube. Then I will send everybody the link, so you can also see from YouTube. Okay. So Tzachi, are you comfortable?
Thank you.
To close the session?
Thank you very much.
Yeah. So, okay, we will close the session. Thank you all participants for taking the time to attend the session. And I look forward to other webinars that we organize, and hopefully you will give us the support. And thank you very much. Nice to see everybody. Bye.